Okay, welcome everybody. This is our December issue of the Ask Mayfield Anything. Thank you all very much for joining. And so, quick introductions, just so you know who we are. So, my name is Ryan Mayfield, founder and CEO of Mayfield Renewables. I've been in the industry since the late 90s and really happy to have Mike Palmer here. Mike Palmer is the Western Region Sales Manager with Megger Americas. And so, yeah, Mike, you want to just give the audience a little bit about you and your role?
Yeah, thanks, Ryan, for the opportunity. It's great to be here with you. I've watched many of these and I really enjoy them. But you never know what's said on one of these. So we love joining and seeing them all. Once again, I'm Mike Palmer, Western Regional Sales Manager for the U.S. distribution products at Megger. We're like everybody else, any test and measurement company. We're really getting into renewables, EV, wind, been in wind a long time. So it's great to be here today and talk about one of the things that we're really gearing up for, because we realize the need to do efficient ground fault testing. So thank you.
Yeah, great. Thanks for joining us. So Mayfield and Megger, we've been working together for a couple of years, and so this has been great. We're trying to really help bring tools and bring methods to the industry and around multiple areas, and the testing tools that Megger produces, and then putting those into use and making our system safer, more efficient. All those kinds of things is one of our goals at Mayfield. So it's been great to connect with you guys. So real quick about Mayfield, we are a technical consultancy and we do system design and engineering. That's where I started the company back in 2007. So we've been doing system design and engineering for over 15 years now. We also do a fair amount of education and training, and then technical consulting and support. So really working in the solar and the solar plus storage industry, working with contractors and manufacturers. So if any of these things are things that sound of interest to you, we might be able to help. Happy to talk with you all at any point. So with that, we will jump in to the topic at hand. So talking about proactive O&M ground fault testing and tools, and really going to start looking at the tools for minimizing downtime. So we'll get into some very specific tools and some things that we've done, gone out in the field, done a little bit of testing using the tools themselves, and kind of how to apply those for different applications within the PV industry. So the whys of the proactive, so we'll talk about proactive versus reactive O&M, and kind of the whys of it might be relatively obvious to the audience that we have here. So, reducing downtime of your PV array and making sure that you're minimizing any costs associated with operations and maintenance is important. And then, of course, improving site safety. So these are, there's probably more whys to it, but on the high level, saving money and making things safer is very important for all of our systems. And so that's one of the things we're seeing more and more of. Mike and I were just out actually at an array, a 10-year-old array, and there's, active O&M going on. And it's become a better situation, I would say, over the, past, half dozen or more years in terms of operations and maintenance, and really focusing in on serving those arrays. The older arrays, I think a lot of times, we still have that mentality of it's a no maintenance item, it's a no maintenance thing, which is just really not true. They're low maintenance, sure, but their PV arrays are not no maintenance. And so I think that's kind of come around to bite some people, bite some sites, just because of that mentality of, set it and forget it. And now it's, problems are arising, people are having to come back and figure things out. So, all of this in terms of the proactive versus reactive, really helping or trying to help keep those systems operating as efficient as possible and safely as possible. And some of the opportunities that we're going to talk about going through and doing these, establishing baseline data. We're going to probably say that multiple times throughout the webinar. I know Mike has got points on that he'll talk about. But that's a very important thing. Watching the health of the array, so we're going to talk about doing insulation resistance testing and some other tests, and being able to look at the health of the system and how it's operating, be able to look at that next year, year over year, and this start to spot trends if there's any issues. And that with that, if you have trends that you can spot, you can schedule maintenance activities, identify potential failures or anything like that. Anything I missed on that, Mike, or anything that you wanted to add?
No, I always like to say that raise your hand if you do something you're not paid for, right? So we tend to not do things that aren't in the spec, and we don't do things that we're not getting paid for. A proactive PV technician, might point things out, but at the end of the day, how much time can you spend on things you're not required to do and aren't getting paid for? So you hit all the bullets there, Ryan. Sorry.
Great. Cool. One thing I'm going to mention this spec over and over again. I don't have a very specific spot to call it out, but as we're going through, I would recommend folks grabbing a copy of the IEC 62446 standard, and that's really about O&M. It's about commissioning and O&M. There's, I think, 2 or 3 parts to that spec, and so that's one that's referenced over and over again. I've seen it referenced in different specs from system owners, things like that, and so that's one that I'll refer back to as we're going along. And so that's just one of, if you don't have that, kind of mark that as put that on your wish list of documents to have, because it will help identify some of these tests, what those thresholds are, kind of what that baseline data needs to be. And as Mike was saying, it will help establish what do you absolutely have to do, because exactly we're not seeing people going above and beyond to do tests that aren't either required or asked for. And so those will set the baseline standards. Okay. So common faults that we have that we're going to really focus here on today. We only have an hour, so there's not just an absolute ton of time here, but ground faults, this is, again, one that this audience is probably pretty familiar with. I would expect if you're attending a webinar on attending the webinar, that ground faults are something that you've experienced or have a knowledge of at least. But at any rate, they are conductors that have an unintentional connection to a metal component. So here we show a picture on the top right. We have a conductor that is getting wrapped around a piece of metal, and that you can tell that this has been installed for a while. And so we have potential here of maybe that conductor starting to get rubbed on that metal. Maybe there's a connection there. It could happen on day one. That's a relatively common thing for modules getting put down on the racking system and somebody torquing down that connection and actually causing a ground fault right there. So it can happen, in the beginning of the installation. It can happen at some point down the line from the installation. So that's what we're going to be focusing in on when we start talking about ground faults, kind of this unintentional connection to grounded conductors or grounded components. And another one that we're going to talk about with respect to doing some testing, and when we start talking about that IEC standard, is actually a lack of a ground connection. And this is one, that picture on the bottom left there. This was the way of doing our equipment grounding connections back in the day before we had UL 2703 racking systems. This was the method. We would take a lay-in ground lug. In this specific case, they drilled a hole in the frame. The marked ground point was actually behind the racking system, so it wasn't accessible. So they drilled a hole in the frame, use a nut and a washer to connect this lay-in ground lug onto the back of the frame, and then ran a bare copper wire from module to module in order to create that bond. And so this was the way that it was done. There's hundreds, if not thousands, of systems that are out there like this. The issue and the problem is, I've seen this time and time again, is those lugs, maybe they didn't use the right outdoor rated lug. They might not have done the right way of making that connection. And so there's a legitimate and real risk here that we don't have a connection to ground, that module is not actually, that lug has corroded, and that, we don't have a great connection to ground. And so that's something that we'll talk about with doing some testing and things like that. Mike, in the sense of, I'll call it the traditional electrical world or something, I think that's maybe, you've had a lot of experience in that. What have you seen in terms of, both either ground faults or these lack of ground connections, how it can relate to our PV systems?
Yeah. So, when we were in the array, many times when we're in arrays, we see this kind of thing, but what sticks out here is dissimilar metals. And over time, that's going to lead to a corrosion path. So even in this picture, you see crimped on lug, you see what Ryan talked about being drilled into the frame of the module. But all those things are points of influence for being open at some point and not being the ground you thought they were. And what does that mean for us as PV technicians? That's also a safety concern. Thinking that everything's grounded 10 years later is not what we should do. And we did some simple tests with the clamp-on earth tester along this whole path in a string, and found out that it was open in a few places. And it was really easy to do, because you started out with really good readings because you've got this huge ground path going every direction into the stanchions and that are pressed into the earth, and all the other connections. And then you find one that's open, and all of a sudden it's not registering anything, or it's registering 400 ohms where it was 5 ohms. So really sticks out at you if you use that kind of tool, and we'll talk about that a little later. But I'm not going to reiterate what Ryan said, other than the fact that you're looking at dissimilar metals here that in a very quick period of time will start corroding and be the source of problems to come.
Right. So we do have some, we're going to talk about doing low resistance ohmmeter checks, and we did it with this exact lug that we're looking at. So kind of circle back on that here in just a few minutes. James, you asked about the link for the standard. So it's IEC 62446. I don't have my normal person on the background helping me today, so I'm trying to talk and drive and do searches and all that stuff at the same time. So I'll get that for you. We'll post it when we send out the follow-up email as well. So get you a link for that as well. But if you just Google that IEC standard, it should pull right up for you. Okay. Okay. So getting into the tools themselves. So we have a handful of tools we want to talk about and get people familiar with. The first two are probably, tried and true. They are tried and true. They're probably on most people's trucks already. But we'll talk about, the specific for the Megger tool is the DCM 1500S. That's a digital multimeter. The 1500S, there's some unique features about it. I think the big things for the solar industry, it can read up to 2000 volts DC and 1500 amps DC. It can do, Mike, correct me if I'm wrong, is it 1500 volts AC and
Yes.
1500 amps AC as well? So
yes.
You have a broad range of voltages and currents on both the AC and the DC side that you can utilize this tool for. And then the other thing that Megger's come out with are quick connect adapters. So when that's an important thing for checking different aspects, somebody's asking about intermittent ground faults, which we'll touch on here in just a few minutes. But the quick adapters are, the MC4 type connectors that you can use if you're connecting directly to modules or strings, things like that. And so those are a couple of the key features. Utilizing the DCM, utilizing a multimeter. This is, I think, one of the methods that people are, it's one of the go-to methods in terms of locating ground faults. And so once you been able to isolate those strings, those conductors, you can check line to line, positive to negative, and then positive to ground, negative to ground. And by knowing what the string length is, and knowing what the voltage of each individual module is, you can use those 3 different points in order to help locate. It's not always perfect, but you can use that to help locate your ground fault. And so that is one of the tools in the toolkit when we start talking about ground fault location. Another one of the tools that is in the toolkit is the MIT 2500. That's Megger's insulation resistance tester. I know Mike's gonna cringe a little bit, but everybody calls it, doing a Megger, measuring your array, measuring your conductors, things like that. So Megger is the trademark name, but the insulation resistance testing is the name of what the test is being done. So we're checking the insulation resistance, and that's what we're showing on the right hand side here. And one of the big unique things on this tool that we're looking at for Megger is it actually goes up to 2.5 kV. You can adjust it, so you can manually put anywhere. I think it's 50 volts to 2,500 volts. Is that right, Mike?
Yes.
And you can dial in. So you could say a 1,500 volts insulation resistance test if you want. And then it also has a guard terminal, which I'll let Mike speak to the guard terminal a little bit, so I don't do it any injustice. But using IRTs, using insulation resistance testers, you can start to segmentize your array. So you can start at a larger value. You can look at the conductors on the output of a combiner box, for example, and then be able to start to isolate. If you have a central inverter, you can isolate different components and start to segment out the different sections of the array so that you are starting big and then going smaller and smaller and smaller to help identify where those locations are for the ground faults. And so that's one of the things that, really talk about with people is trying to, on the troubleshooting side, segmenting out the array like that. But yeah, Mike, what did I miss on the MIT?
Well, I was thinking while you were talking that inverter diagnostics have gotten, light years better than where we were 25 years ago. They're better, but they're still, they don't nail where the trouble is. And our technicians, PV technicians, give them credit. They've got their sequence of ways to find these faults. And I think it's all about sectionalizing and using the what's in your toolbox to do that. You hit on all the points, of course, but I'm always amazed that when we're at conferences and of course NABCEP when we talk about the guard terminal, how many people don't even have never used it, and you don't need to use it unless you have to, and when you have to, it can really save the day. And what I'm talking about is you can go through your testing on many inputs out of the combiner box, and you can have 200 gig ohms everywhere you go, and then all of a sudden you got 1 kV. You got 1,000 ohms where you were reading 200 gig ohms, and you go, what's going on here? Do I just have a bad conductor, or what's going on? And then you think about it and you go, well, I've got a lot of surface contamination from salt, from mud, or whatever, and you find out that you've actually got a lot of readings that are that far off. So we've put out, with the help of Mayfield Renewables, a lot of content on how to use the guard terminal, but you can actually wrap a piece of number 6 ground wire around the whole bundle, and you can sense the surface contamination using that blue test guard test lead, and it'll save the day because you really don't have a problem. You just got surface contamination and leakage from a Megger test. So, just understand that, only our big box units had those forever, 5, 10, and 15 kV. And now we have the ability to have the guard terminal in a handheld device. And, when you're carrying all you're carrying now, that's, you could fill a back of a golf cart with, it's nice to have a handheld with that with that guard terminal on it. And once again, you're not going to use it every day. Some of you may have bought this unit and have never used it yet, but it's there if you need it. It'd be great to get some feedback in the Q&A if anybody's got to that point where they've had to use a guard terminal. But I think, our PV technicians have figured out a way to sectionalize at the string level and then go module to module or section to section to figure out where their trouble is. But everybody has to admit it's the longest endeavor we do in troubleshooting. And, ground faults, that's our future. We're going to really work at Megger on making it easier with content delivery and tools that'll allow you to find ground faults faster and until those inverter diagnostics catch up. So anyway,
right.
I'm good with this one.
Well, so there was a question that came up before this webinar even started, and so it was around the destructive, if doing insulation resistance testing, if it's destructive. And Beryl, I've seen that you're on the call, so if you want to clarify that question, if I'm not getting it quite right, but I was understanding that question to being on the cable system itself, doing multiple IRT tests. So you're going to put, or maybe once a year, or maybe every 6 months, depending on what your protocol is, that you're putting this high voltage, you're putting that on the conductors, and you're doing this check. And so I guess that's the big question, is this a destructive test over time? And I guess I should preface that with the expectation that you are not doing this through the modules themselves. Module manufacturers, I have yet to get, I know people do testing, the IR testing, insulation resistance testing through the modules. And it's getting that okay from the module manufacturers. That's one of the things that you should be doing if you're going to be doing it. And some people have gone that extra distance, some people don't. And so I guess back to the destructive element of it, Mike, if we're doing these tests, is that something that should be concerned? Are we degrading our conductors faster by doing these tests?
Yeah, that's certainly one we get daily into the application engineering group. And we've heard it all as far as, obviously it's a de-energized test. So, we're doing a IRT test on a de-energized circuit, but that panel sitting in there, there is a possibility, and the module manufacturers have told us, that is a possibility. So we just take the line of caution, and I think I answered in an email, and I don't know if our viewer has gotten that yet, but we just take the cautionary step and say, if you can IRT test, and I know it's hard because we want to put the loop together with the modules and the cable, but if there's a way we can do the testing, before all that's put together without the module in the loop, it's certainly the way to go. But on the side of caution, we always recommend that you check with the manufacturer. And to be honest with you, they've been really good about getting back to you in a timely manner. And I can't tell you which ones. We've talked to them all. And typically what I found is about half of them will say, no problem, go forward with the test. And then some of them say, you better be darn careful. And we certainly never want to violate the voltage on our string and on our array. So we keep that. If it's a 1500 volt string, that's what we're testing to. And that's another reason for the MIT 2500 in a handheld. Obviously, you can do that test using a variable voltage unit to do that and assign that 1500 volts and never go over that, because it will stress the cable. But think about what an array is doing over its lifespan. It's stressing the cable daily, with the activity from the sun and the energy we're producing. So not a cautionary thing for the cable. It's built to do that as long as we don't have any faults in it. But on the module side, I think there is a cautionary, and there's people on this call that have been testing through the module for years. There's no surprise there. Of course, Ryan and I have never done that. So, but I think for the most part, cautionary is the best. The cable itself, straightforward, do it up to the voltage limit of the array. And then, when the module is tied in, err on side of caution to get approval. So if something happens in 2 months, you're covered.
Sure. Great. And so then there was a question about intermittent ground faults, and this question that just came in about, ground fault more prominent when the environment's wet. And the IEC actually in that standard 62446, the IEC talks about this exact scenario, intermittent ground faults. And there is actually a wet test that they recommend. It's kind of the second level of testing, if you will. If a problem is arising and you don't find it this way, this is kind of that next step. And so actually getting the array wet, getting the conductors wet, and doing your testing in that sense will help exacerbate any potential ground faults that you have, and to help identify those. So again, if you can isolate strings, you can isolate different sections of your array, and it's on a multi-megawatt ground mount system, getting an entire, getting everything wet is maybe not the most, it's not the easiest thing to do. It's much different in a small commercial or residential type application, but that is a way of trying to pull out that intermittent aspect of it by doing some wet tests. And so those are, again, in that IEC standard. Would recommend taking a look at those in terms of doing those tests.
Just a quick,
Sure.
We actually did this 8 years ago, if you remember, Ryan, with before we had the 2500 on the 1 kV in it, and it was the aha moment. We were filming for, I think, one of your college that you were helping with curriculum, and you took a water bottle. We did the initial test because you want to do that. You want to measure this string dry, and you want to, because that's its life. But you also, if you take a water bottle and you pour that on some of the modules, you'll see immediately that path. And that's what we're talking about when the array's wet, how it changes everything and where we see more faults, because we've created that path to earth, right? With water, it becomes, you don't want to believe it, but it's a path, it's a conductor, and it helps us make that connection to ground. And we're vulnerable then for any faults that are in the array, in the string, and also, lightning. And I'll talk about that in a second.
Sure. Great. Okay. So we're going to move on to some of the other stuff. Of course, you'll get all of our information if there's additional questions, things like that you want to talk about more. Happy to do that as we move along. So one of the other tests, I should say, and there's Megger has a tool that's out there. And this one was, I'm going to be, honest here. This one was relatively new for me. I knew vaguely of this, but the application was, a few months ago when we were starting to work together, or when we started working on this, this most recent project, digital load resistance ohm meter. And so, Mike, I'm going to have you kind of just talk us through, what this is, maybe where it's been different. And I think this is the tester getting back to that picture where we showed the lay-in lug that was getting corroded. We were in the field using this tester, and just for reference for folks, and it was a ground mount array, old, like 285 watt modules or something like that. And so we had lugs from module, one module on one side, another module on the other side. So less than 3 feet of distance between those. They were connected with a bare copper, and we were not able to get a continuity check on those. And so I'll have Mike kind of explain this a little bit more. But I think the thing I want to just kind of point out, or ask you, Mike, to kind of wrap into all that is, how is this? You asked me before, how do I check continuity of my conductor or my components when I'm in the array? And I told you, I just pull out my multimeter and I ring it out. I just put it on the continuity check, and I turn the ringer on. If I hear that ring, then I say, okay, I've got continuity. So I guess talk to us a little bit about what the DLRO is, what it does, and I guess how it's different, or what it brings that the multimeter doesn't have.
Yeah, so in the code, and I think you mentioned that earlier, or maybe you didn't. This is a good time for it. We talk about making a continuity test to make sure that you've got a connection, an electrical connection between 2 points. Everybody probably already knows this, but if you didn't, that multimeter has less than a tenth of a microamp of worth of current that it can flow to make that test. And by the way, everybody's on the buzz feature of the continuity check, and nobody's looking at the reading on it. Raise your hand or send us a Q&A that you always look at the number on that continuity check. And, it won't surprise us if nobody says they know the number that's achieved with doing that continuity check. Low resistance measurements, on the other hand, is all about the reading, and it's all about testing that connection. So, it'll show when degradation is occurring in these electrical elements. And the best thing that I can refer to is a bus bar. Cable lugs landed on a bus bar, and that torque connection that put it there. And we torque it for a reason. We want that to be at its best at commissioning, but typically we never look at it again. So we don't know how good it is 10 years later. And I know that's not the picture we showed. We could have showed bus bars. And I travel with the bus bar using the DLROs to show the difference of one that's lugged down tight on torquing and one that isn't, and what happens. And, the big thing that happens if we don't make sure that connection is firm is heat builds up. And what's bad about the heat building up? It ruins things. So, the specs are lagging with what we need to do on O&M to shore this up. And you're going to hear more of this from us in detailed DLRO testing at NABCEP. We've got our renewable engineer out of the factory in Dover, England coming, Felix Lesmes. We're excited about it. We're just touching it here in this podcast, and I was thrilled to be able to do it. But think of a battery strap on batteries. Think of that bus bar connection. Those change in measurements of the DLRO, and a DLRO measurement, just to get into it briefly, is a 4-wire Kelvin test. So we're going on both sides of that connection, and we're flowing current. And the handheld that's in the picture here is a 2 amp DLRO. This came to existence really in the wind segment with testing the electrical connection at the turbine blades all the way to earth. And so we have a cable reel with over 300 feet of DLRO cable on it to do this test while our rope partners are hanging 300 feet out of the ground. You used to have to do this test in another way with a big box. Now we got a handheld, and we're going to start talking about using that DLRO2 to test these connections. And at the end of the day, it's really safety as well. But the other thing that affects these connections, I mentioned it earlier with the dissimilar metals, but we have temperature, we have the corrosion that occurs. We've pretty much hit it all on what the low resistance test will do. But there again, we have 2 amps, 10 amps, 100 amps, 200 amps, up to 600 amps. We're not using that, of course, on such small connections, but we use what's needed to tell us a historical measurement from commissioning, and just so you know, commissioning could be 10 years later because you never did it the first time. It could be today, and it could be 10 years later today. And that's our line in the sand that we're going to start at to test these connections. And also what we really need to zero in is technicians' safety in the array. Probably a term you don't hear a lot of. When it's lightning 3 miles away from the array you're in, you're still at risk because of ground potential rise. So this is all things we're going to talk about in more detail. You'll see in the coming year, especially at NABCEP. So that's the best I could tell you with limited time today on DLRO testing. Nobody's doing it unless it's inside the inverter, maybe on bus bars for both grounding and power cables.
Yeah. So the two things that I would bring up in terms of this test specifically, is, one is we have our UL 2703 racking systems now. And we showed that picture earlier of the ground lug, connected, somebody drilled and connected a ground lug to the back of a module frame. We're not doing that anymore. We have 2703 racking systems where the mechanical connections are making the electrical bond. And if you go and look at that spec, there is a check that in order for the racking manufacturers to, pass their UL listing, to get that, to be able to stamp that as a listed product, they have to pass current from that grounding point through to the racking system. So they do have to they pass current through and measure the resistance, and the resistance has to be a tenth of an ohm or less. So 0.1 ohms or less is the threshold. And the interesting part for me is the IEC standard I keep referring to talks about doing a continuity check. It just says I think it's a 2-sentence part of that standard. Really just says you need to do it. And so there's no spec to it. There's no like pass fail number or anything like that. And so this gets back into what Mike was talking about, or what we've been talking about, setting that baseline, taking the reading when you're commissioning, and now you know what that value is, and then be able to watch that over time and making sure that what you are expecting is a low impedance path for the ground connections is not, you're not getting high resistance there. And so that is, one of the methods, or one of the tests I think should be incorporated. It is something that IEC calls out, but it's not real clear on exactly how to do it. So question just came in about the DLRO. So while we're here, before we leave it, so would you recommend using a DLRO to QC PV jumpers that are assembled en masse by a field crew? No matter how much instruction we provide, there's always installers who screw up NC4 crimps. This was exactly where like my mind went when we started talking about the DLRO and all those things. At this point, I haven't been able to like confirm or have a positive way of doing that test. But I think I still see that as a possibility. I've been talking with Stoibley about this and some other folks. And, at this moment, I don't have a yes, no answer for that. I don't think it's a bad idea. I'm not sure that the way that DLRO works may not be the exact best test, but we're about to talk about TDR as well. And there's some possibilities. They're not perfect as well, but some different technologies on the TDR side that might work for that as well. Mike, do you have anything that you might say to that?
Yeah, I wanted to make sure I got in that, DLRO testing is 1 ohm or less. So think about your multimeter. It's not going to go there. It's not going to go in the micro ohms. So we're below 1 ohm when we're doing this kind of testing. And for repeatability, we have to be able to have a test and measurement unit that will go down into those micro ohm areas. But as far as the connectors, stay tuned. Not going to tip the hand, but we're looking at this with the connector manufacturers, and we think it's a viable option for helping technicians make this test very quickly.
Yeah, and I think as far as the connectors go, I think one of the biggest hurdles to get past is the energized aspect. So if you're checking connection to connection, in an array or a string that has voltage present, the tools, most tools don't have that ability to do it measuring on a live circuit. So that's one of the biggest hurdles to overcome on that. And again, this is, checking a few connections on a residential application is much different than checking, thousands upon thousands in a utility scale. And so this becomes a matter of quick, time. I know it's a efficiency and I know it's a safety thing, but it's also crews are trying to move fast throughout the array. So that's another aspect, another thing that trying to do it quickly is an important part. Okay. So I threw out time domain reflectometers, or TDRs. So Mike, why don't you, this is one that I feel like I'm still learning a lot about this. And so I'm going to completely defer to you, but so talk to us about a TDR. What is a time domain reflectometer? And, how is this used to find faults on, our more traditional electrical systems, or, three-phase cable assemblies, things like that. This is a tool that I know folks are out there using. So how can we incorporate this into the PV world?
Yeah, it's something we talk about every day with customers that call in and say, what's the right piece of equipment? And they really do have their place in what I call the low voltage world, forever. Telecom, cable TV, and electrical, as you mentioned, especially three-phase cable. But what we see in PV is that distribution side, or that DC side, going from the module, from the strings back to the inverter, is typically a one conductor cable. And what TDRs do is they send a low voltage pulse into the cable under test, which is typically two metallic paths. And they look for any impedance change within the cable. And if they see that change, they reflect it back in the way of a trace on the screen that you're seeing on your screen right now. And I'm not going through all these, so don't leave the call. The top two are the most prevalent in what we look at, and that is open conductors and short circuit conductors. So a ground will appear the similar way as a short on the TDR screen. And there's many more here. Typically, when we see water get into a cable, a power cable, whatever kind of cable it is, telecom, whatever, you don't dry them out anymore. You typically find the wet spot from both directions, and you dig it up and replace that wet section of the whole cable. But in PV, and I mentioned the DC side, where we have USC2 type cables, as we all know, there's only one conductor. They're usually direct buried. They're not in the conduit. So we have other means at Megger to find those faults. It won't be a TDR because we don't have two distinct paths running in parallel with one another like we do in, three-phase cable that Ryan mentioned. So, in that scenario, we hook up the two test leads to L1, L2, L1, L3, L2, L3. We make a comparison. We look at the screen and we say, what kind of fault am I seeing? If I'm seeing the far end, life's good. If I see a short, well, that's where my trouble is, and that's where I'm going to. But on the AC side of the inverter, typically it is that three-phase cable, and we can use a TDR, very, very quickly. And Megger has all kinds of TDRs, different lengths, different setups with cabling or test leads, and very, very, high-end type of testing at a lower price. For our top of the line, which is the TDR 2050, that's mostly used in the electrical world. So any impedance change, once again, in the cable will cause some energy to reflect back towards the TDR, and you kind of have to think about it as radar. The TDR regular radar, a ping is sent out, and then the transmitter shut off and the receiver kicks in. And it looks for that impedance mismatch on the screen in the way of a change in trace. So if you could kind of think about it as radar, and as the pulse travels down the cable, any change will reflect back, and that's really what TDRs are about.
And so, TDRs are pretty new to me. So for those that maybe aren't super familiar on the call, so let's just focus on maybe that short circuit, the second box down there. So that is, we're essentially looking at a length of cable, right? That will tell us a distance. And so the TDR is sending a signal on that cable. And once we know some cable properties, this is something that, you put into the TDR when you're setting it all up, give it some cable properties. It can actually give you essentially a length to where that fault is. Am I saying that right?
Yep, right on. It's exactly what it is. And, it's like any other tool we use. We get used to using it. And then, we sell these all over the world in different industries. And the technicians get really, really good at it, and they surpass my particular expertise, even though I've been doing it for a long time, based on their industry. And it's amazing. Oil and gas, offshore oil drilling in the Gulf. I mean, it's just amazing who uses these, but there's a place for them in PV. And we saw a lot into the PV industry, but you nailed it. You know, that impedance mismatch and that reflection back is what you're seeing on those top two boxes here for opens and shorts.
Cool. Yeah. So this is a way, and when I found out about these, and I think as others have, I've talked to others in the doing O&M work, wouldn't it be nice if these could work on our single conductors? They're just not this technology, this specific technology is not quite the right application for our on the DC side, because to that point of, if I could just put it on this cable and I knew that fault was 250 feet away, I could just go paste that off and go find my ground fault and fix it and be done. Unfortunately, life's not that easy for us, but as Mike mentioned, we're all trying to figure out some of the things, and there are multiple types of TDRs out there. So it's a good tool for the right application. And right now that's, over on the 3-phase side, when you have those 3-phase cables. Okay.
Yeah, we do have other products that'll do those single conductor cables. That's for another session.
Sure. Okay. So the last one I wanted to talk about, is to get into the ground testing. And so digital earth testing, again, this is one that's, maybe a bigger topic. But Mike, talk to us about, this verifying ground continuity. I put in here that, this is typical of substation work, and I think you might have a little bit of a caveat on that. And then the next slide, we'll talk about the fall of potential, kind of what that means. But talk to us how this might get implemented in PV systems, and, what are we checking for when we're looking at our, using a digital earth tester?
Yeah, so in the picture here, we actually have two different pieces of equipment. On the top right, over to the far side, is that clamp on earth tester I talked about earlier, where we got various readings on both sides of those module connectors, and it was a very quick way to see what had a continuity ground and what didn't. So that's a split clamp there that's going to put a pulse out, return it back through earth and the attachment elements of the array and back to earth. So a clamp on earth tester is a great device to use to quickly go through the string and find out what has good grounds on it, what doesn't. But in the forefront picture, the big box, and then you see two clamps there. Those two clamps are that clamp on earth tester, right? But they come in that kit, and they become a clamp on earth tester because it's got a current and voltage probe. So that's all a kit. That's our all-in-one ground tester. And typically, that was created a few years ago for the filtering that's needed in substations because of the noise. But it's also all of our ground testers in one. So if you're looking for a solution that has all of our ground testers, because you never know what you're going to need, this will do everything: soil resistivity, 2, 3, and 4 probe testing, fall of potential we'll talk about in a minute. But really, in the substation, we can use the clamps to go element to element, switch to switch grounds in the substation, and just measure continuity there and see the low resistance that's encountered, or if the resistance is higher, then we know we have a problem on that particular switch or stanchion. So when Ryan mentioned the substation, you got a grid. Even in a solar PV array, you have a substation. In most cases, some are direct connected, but you still have a ground grid in that sub on the PV array. So you still need the type of tester that has the filtering ability, like the DET 2.3, to do the testing that's needed inside the fence.
Yeah, and so this is not something that I'm familiar with doing on smaller scale systems. As we're getting into these large systems, as we've been talking, where there's a substation involved, this is where we're really starting to see these tests being performed again, because it's a requirement, and it's very often written into the spec of verifying the grounding system at the time of installation, and then annually, probably as a minimum, in order to maintain when at a substation level, medium voltage levels, you have a problem with your grounding system, it's, can be catastrophic. And so this is a really important thing that we're looking at there. Okay. So I have just a few minutes left, but I think we're doing great on time. So just want to talk about, you mentioned follow potential. And this is one of the things that the DET 2.3 can handle. So kind of tell us, what are we measuring on the follow potential, and how is this useful for the technicians?
Yeah, it's another question we get all the time, and you're not going to come across this except on the inverter side usually. With which the NEC code states 25 ohms or less, correct? So,
correct.
You're going to need to figure out how you're going. What's that? Okay, so you're going to have to figure out, how do I get to that 25 ohms? So typically, what every contractor is going to do is a follow potential test, and really what you're looking at here is you're looking at the electrode there on the left, which is the one either feeding the bus bar ground location in the inverter, and you're going to put one probe, one test lead on that. You're going to stagger the test leads out given the area you have to work with, because as we know, the footprints sometimes are limited or in and around the inverter. So typically your electrodes, ground rods, in other words, are going to be at the inverter, or you could have U for grounds, which are made out of concrete and steel and feed the bus bar and the inverter. But this is a follow potential test. The center potential probe is 62% from the electrode to the current probe, which is the far one on the left. It's a real easy test. Our Getting Down to Earth booklet, this is the mainstay of it, using this follow potential test to calculate that 25 ohms that you're going to need to acquire as per the spec for your commissioning report.
Cool. Yes, I know, in 3 minutes, we can't really give everything about this, but Megger's put together some really good information on this. And again, this is, much larger scale type applications. Your 100 kilowatt ground mount system, probably not going to be utilizing this, but wanted to bring it up, kind of discuss it as our system's getting larger, as our O&M, our commissioning procedures are getting more and more detailed and comprehensive. Just a good thing to be aware of. Okay, so kind of some of the key takeaways. Just wanted to, reactive O&M, specifically fault locating, it's not something you can ever get away from, right? It's gonna happen, and it's just a matter of it's going to be part of any sort of O&M application. Of course, if you can be a little bit more proactive about it, into your annual maintenance, those kinds of things, you'll be able to maybe identify some of those and limit the amount of reactive aspects you have going along. So we talked about a number of tools that can get incorporated. Some of them have some very specific applications, but it's good just to kind of understand what the breadth of those are. Some of those were new to me, so really excited to kind of be bringing those to light for others as well. And then I know we've said it time and time again, but the establishing trend lines, it's important for future maintenance. So all of these aspects, the insulation resistance testing, that DLRO, voltage measurements, all those things, you can create logs, you can create trend lines. And so you can be looking at your system over the course of time to better understand how it is, or how it's operating, and, maybe where it's going, and be able to cut ahead of some things and be able to maybe do some maintenance on it that you see for coming ahead of time. Okay. So Mike mentioned this earlier. We're going to be at both Megger and Mayfield will both be at the NABCEP Continuing Ed Conference. That's in March in St. Louis this coming year. So we'll have a lot more information. We have 90 minutes there. There'll be some tools on hand. We'll be able to do some more hands-on kind of stuff. And so if there's additional questions, obviously you can reach out to us before then, but this would be a great opportunity if anybody's going to NABCEP in order to see and learn some more. And then finally, here's how to get a hold of us. We really appreciate your time. We appreciate the questions, paying and giving us part of your day here. So any questions that come up or maybe or spark some interest or some things like that, you can reach out to myself. You can reach out to Mike on any of those, and we'd be happy to talk. So, Mike, is there anything else that you have for the group?
No, thanks so much for the opportunity, and of course, happy holidays and happy
Yes.
New Year to all of our partners.
Great. Thank you very much, everybody. I appreciate it, and we'll talk to you soon.